Morning. Thanks for being here at the workshop. As I said, my name is Kris Shinn. I'm the VP of Engineering at Infura. For those of you who aren't familiar with Infura, we started back in 2016 providing Ethereum node JSON-RPC access to projects in order to get them up and running into mainnet as soon as possible. They could use our service back then to get to mainnet without having to spin up nodes, maintain those nodes, sync the nodes. And as the Ethereum ecosystem has evolved, our product has evolved with it. So in addition to Ethereum access, we also give access to L2s like Arbitrum and Optimism, other L1s like Avalanche and Near, IPFS, and we've also started releasing higher level APIs like our NFT API that allows projects that are dealing in the NFT space to get to production really fast. Now, the title of the talk is Level Up Your RPC Game. And there's three things that I want to get out of this workshop in the short time that we have. One is a deeper understanding of the RPC. So I'm not going to cover the breadth of the RPC. I don't think that would be a very compelling workshop. But we'll dive deeper into specific methods in the RPC and explore how you can use them, the kind of things that you could use them for at sort of this lower level. We're going to be using Foundry's Cast to explore the blockchain, and I'd highly recommend you guys add it to your toolkit for RPC, and I'll try to make the argument why in our workshop. And finally, in order to deal with sort of the state areas of the JSON-RPC, we're going to be using ENS as a case study of how we can explore into the RPC. So we'll do a deeper dive into ENS and how that works as it's relevant to RPC. So it's easy enough to follow along. If you want to follow along here, or if you want to follow along after, all you need, everything I'm doing here is covered under the free account. So you would just need to log in or register at infura.io, create a project, grab that Ethereum mainnet URL, and then plug it into Cast, plug it into your CLI, and you're ready to go. So starting off with level 1. I want to make an argument that the CLI is really where we want to be when we're exploring the blockchain. And in doing so, we'll explore some of the basic methods of the RPC that you're probably all very familiar with. So why do we want to stay in the command line? It's really about the power of REPL, right? It allows you to get fast feedback. It allows you to just play with ideas and work stuff out without having to context switch between tools, without having to compile and run on the command line. And within at least the Unix-style CLI, you're able to pipe these into other Unix tools to really start harnessing power of various tools in the ecosystem. So this is what it's like starting with curl, right? The first time that you get an Ethereum endpoint that you want to connect to, this is probably the first thing that you're typing out, right? Get block number. And as you can see, this is my actual typing speed. It's really tedious. There's the JSON payload, JSON request and response envelopes that you have to include every time. You have to handcraft these JSON-RPC objects. And while it's supported on many systems, while curl is supported on many systems, and you can cut and paste from just about any example on the internet, this is a kind of tedious way to work with JSON-RPC. So the next level that you would probably go to, or at least that I went to, is using something like Postman. Now Postman is great because, as you can see on the left here, I can save all of the method names that I might be able to, that I might want to use. In fact, some of these Postman files are around on the internet, so you could just import it and have them all ready to go. It has a template for all of the JSON-RPC payloads, so I don't have to type it out every time, and I can just change the parameters that I want. But the issue is that's a standalone tool, right? I can't combine it with any other tool. I have to context switch into this program, and it's very limited what I can do with the input and the output. So then, if you're like me, just jump straight into code. Let's get a TypeScript environment going to, check what the latest block is, for example. And this is great. Again, there's a lot of examples on the internet. Ethers.js is a great library to work with, and it's really powerful. You can do anything that you want. But you have to bootstrap a project to get it going, and you have to do sort of the run compile or run code loop, right? So you're constantly switching between tools. So going back to the JSON-RPC, this is what a get block number looks like, right? Everybody's probably typed this or copied and pasted it in this room. And it's a fairly simple method. No params that you have to worry about, but it's still pretty tedious to type out, as you saw on that last slide. Did I forget to send the header? Did I make a typo in the name? There's a lot of ways that this can go wrong. So with cast, all you have to do is, there we go, really just type cast block number, pass in your RPC URL, and it returns you just the RPC number. No unwinding JSON-RPC payloads or response payloads. Now it's kind of tedious to put this in every time, so you can actually export it as a variable, and cast will just grab that whenever you use it. And so for the rest of this workshop, I'm not going to be specifying what the endpoint is. I'm just going to assume that it's in your environment already, and we're just going to work with the cast tool. So stepping up one level, block number is nice and it gets you what the current head of the chain is, but you can't do much with it, right? So get block by number is usually the next command that you're going to be typing into the blockchain to pull back like whatever block you're interested in. And here's what get block by number looks like. As you can see, this one has parameters, unlike the last command, and you have to remember to pass in two parameters into this method, right? The block number that you're interested in, and whether or not you want the block bodies, the transaction bodies returned with the payload. Now, the bad thing about this is it's not that complicated, but there's also no defaults. So you have to remember to pass in both, regardless of whether you're interested in getting the params, the transaction bodies or not. Within cast, it's pretty easy to pull back the block number. All I want is the latest block, and I get the whole block returned to me in a somewhat human-readable form. Now, you can't really see what's going on because it's scrolling way past my window. But one of the cool things about cast is that you could actually pass in a field. If you're only interested in the block hash, or you're only interested in the state root, you could just pull those out of the block without having to parse through the entire block return, which is a pretty cool feature. I'm going to let this run through again, just so you can see it. Here, what I want you to notice is I'm not using block, I'm using an alias shortcut, right, BL. And if you looked at getting the block number, there's an alias shortcut BN, which reduces the amount of typing, it allows you to type these commands faster and work faster within the command line. Now to round out level 1, we're going to step up a level in complexity in the JSON-RPC methods to do get logs. And this is a fairly simple get logs command. The params that you're putting into get logs is a filter block, right? A filter object, in which I'm not specifying all of the parameters here, but you have to type in what block you're interested in. You can include topics, you can include address. There's sort of a number of different ways that you can format this block, and it's really tedious. If you're typing this out on curl, there's a million ways for this to go wrong. And for me, it always goes wrong in those last braces, right? Like square curly, I almost always invert them, I leave one off. I always have to retype and retype this until I get it right. I always type this command and I hate it. So cast doesn't give you the ability to get the logs by itself, but it does have an RPC function where you can basically pass in any RPC method. So here, I'm getting the block number, I'm casting that to hex, and then I'm using the RPC command, right? RPC, the method name, and then the parameters that you type out. So yes, I'm still typing out JSON on the command line, but it's a lot simpler than it would be if I was to use the JSON-RPC. So here, I'm basically getting all of the transfers in this particular block, and I can pipe it into JQ if I only want to know like how many transfers there were in that last block. So now you can take the output from JSON-RPC and start piping it into other tools that allow you to explore and work with this data without having to go into a programming environment, which in my mind is pretty cool. All right, so we explored some of the basic RPC methods in level 1. In level 2, we're going to be exploring more of the state. and specifically around ETH call. And in doing so, we're going to introduce ENS, and we're going to take a slight detour into the inner workings of ENS in order to pull this off. So what is ENS? ENS is a distributed open extensible naming system based on the Ethereum blockchain. I pulled that off of their website. That's not my wording. Essentially what it means is that it takes human readable names like Shinn.eth, donations accepted by the way, if anybody's so inclined, and it transfers them into a bunch of different types of data on the blockchain. Ethereum addresses, content hashes if you want to point to something in IPFS, it can point to ABIs, or it could store any arbitrary metadata on-chain and accessed on-chain, so you don't have to cross it with any sort of decentralized Oracle networks or anything like that. Now, there's a lot of support for ENS built into tools and libraries already, which is great, and Cast is no exception to that. So ENS done the easy way. You could just resolve a name using Cast. So here I'm resolving my name. There's the Ethereum address. And I can do the reverse lookup within Cast as well, where I can find my name based on my address. So it's really easy to work with if you want to probe in like where names are pointing to, what's stored behind those names. But what's really going on behind this is what we'll dive into next. And to understand that, you have to understand how ENS works. So ENS is basically a two-component system. There's one contract that governs the registry, the owners of the names, essentially, and then a second contract that resolves those names. Splitting the architecture like this makes it really a really nice feature to be able to upgrade the resolver to add features to ENS without needing to redeploy a bunch of contracts. All you're really doing is changing the resolver contract in that registry, and you can upgrade the name. Theoretically, you could write your own resolver contract, upgrade ENS to point to it, and add custom functionality of your own, as long as you pay attention to implement the standard interface. So essentially it's a two-call system, right? This is what's happening when you do resolve name in Cast. It's calling the resolver method on the registry contract to get the address to resolve. Then it's calling the adder method on the resolver contract to get you back the address that's registered for a particular ENS name. Now, the third thing that we have to dive into with ENS is the name hash. So nothing in ENS is stored with plain strings. Like Shin.eth is not stored on the blockchain. It uses a recursive hash that maps to a bytes 32 type, as you can see in the method spec, in order to reference everything within ENS, right? So there's a bunch of different reasons to do that. One of them being that it's very difficult and expensive to do string comparisons, to do those name lookups, where you can do sort of an atomic bytes 32 comparison. It's much easier. It's efficient to store. It's efficient to look up. I'm not going to go into the details of how name hash works, but I'll publish my slides on Twitter after this, and if you want to look it up, I have links out to various documentation here. Last thing I wanted to mention that if you look through the contracts, it's referred to as a node in ENS. That bytes 32, that name hash is a node. So now we get to ETH call, back to RPC. So this is what the ETH call would look like to get the resolver contract from the registry. Pretty simple, right? You specify the to contract, the data, the call data, and then the block number that you're going for. This payload to me is too onerous to type out. And it has to do with that data line. I don't have the 4-byte signatures memorized, and certainly I don't know. It's difficult for me to encode the parameters on there. So at this point is when I would usually jump to code and just start like importing the contract ABIs and working within code. But you can do this in the command line now with Cast. And by the way, Cast gives you the ability to calculate all of the call data. You can calculate the call data. You can look up, encode, and decode 4-byte signatures. There's a lot of functionality there. But we don't have to do that for this particular example. So here you could see that I'm calling the name hash. This is what the name hash looks like that's stored in the contract. And now I'm doing a Cast call to the registry. I'm calling the resolver method on that, and I'm inlining the name hash in a subshell. And that basically does the Cast call to return the resolver contract. Now I'm doing a cast call on the resolver contract. I'm looking for the address, that method signature. Again, subshelling my name hash. And what we get is my address. And we can check this by calling cast resolve name kshin.eth, which is pretty cool. So we basically manually did what cast gives you the ability to do. So why would I want to manually go through all of these steps in order to resolve the address? Well, if you recall, like ENS can store different types of data. Resolve name really just resolves the adder. So if you wanted to say, see if I had an IPFS hash pointing to my website, or if I had metadata stored on chain, you would have to do this manual call, subbing out that adder with the right method. And you can manually resolve multiple types of ENS names. So level 3. We've been through, we discovered a little bit about ENS. We've done some calls growing in complexity. In level 3, I want to dive deeper, and this is going to get more into the guts of the storage system of Ethereum. But we'll explore some methods that maybe you don't use every day, and again, within the context of ENS.
I can't use a wired com.
So here's what a snippet of what the contract looks like. The ENS contract is fairly simple. The resolver contract is fairly simple. And there's 3 things that I want you to notice in this contract. The first is that this main mapping, this first variable here, is a mapping between the bytes 32 node and the record, that record struct, right? The second thing is that this variable is the first variable to appear in the contract. And what that means, and I'm not going to go into how Ethereum manages storage, but that effectively means that that's going to map to storage slot 0 once it starts calculating out the contract. The other thing that, the last thing to note is that if you recall, Ethereum stores in the state tree fixed width 32-byte slots, right? So everything fits into a 32-byte slot or multiple 32-byte slots, and this record struct is no different. So once you calculate an index, there's the 20-byte address, 0 padded to 32 bytes, the resolver address, 20 bytes, 0 padded to 32, and the TTL, which we're just going to ignore for the purposes of this workshop, as that third slot. So now we calculate a storage index. I don't know if any of you have tried to do this before, but it's a gigantic pain in the ass. It's pretty complicated in how to do this, and again, I would have to jump into code in order to calculate this. But CAS gives you the ability to calculate the storage index. So I know that it's a mapping with a bytes 32 type key. Here, I'll put this up here. The bytes 32 type key, the value of my name hash, and storage slot 0, which is what we covered when we reviewed the contract. And what gets returned is that giant hex string of where in the storage tree this is actually located, which is pretty cool. Because it enables us to do something like get storage at. So now get storage at is a fairly simple method. Again, the parameters for it are the contract that you're looking to call, the index that you're looking to call it on, and the block that you're looking to pull it back. And what's interesting about this particular method is it sidesteps the EVM. It's like doing an ETH call to get back like a pure view data, but you don't have to invoke the EVM. You can just go straight to the database, straight to the KV, and get it out based on that giant index key. And this is useful for exploring what the storage layout looks like, as well as it's useful for proofs and going down that line of the Ethereum space. So again, CAS gives us the ability to do that. Same params, storage, the contract, the index, and it defaults with the latest block. Now what I want you to notice here is I'm taking that return address, which is the owner, by the way, and decoding it using ABI decode. Here in this next storage, I'm incrementing that storage slot by 1 because it's the next record in that struct, and it returns me the resolver contract again. So as this loops through again, it went by pretty fast. I'll let it sink in as we do it again. This accessed the start of the record, so this is giving me the owner address, which is that 74AA. I'm decoding this using built-in tools just to get the address, chunking off the zeros. I'm incrementing that index by 1 to get to that next record. next field in that record, and again using the utilities to decode that. So like now we're getting more and more manual, right? Rather than just doing the ETH call, this is actually going straight to the database to get the answer. Similarly, you could get proofs this way, right? Get proof is sort of like get storage on steroids. It'll return you the values, but it'll also return you the Merkle proofs needed to reconstruct the verification side of things. Now, again, the arguments here are the same as get storage, the contract, the index, and the block. But what it returns to you is a bunch of fields related to the account, in particular, and all of the Merkle proofs. And it'll return to you the account proof as well as the storage proof if that account is a contract address. Now, the Merkle proofs aren't as useful on the REPL. As far as I know, there's nothing that'll take the output and create a Merkle tree, but it sounds like a great project to hack on if anybody's looking for stuff this weekend. Here's what it looks like with cast. So cast proof, again, the contract, the storage index. I'm piping it into JQ for pretty formatting. One thing to notice here is that it returns a lot of fields. So if I only want to pull out specific fields in that payload, again, I can use JQ and just return the things that I'm interested in that payload. Now finally, a really cool thing is this transaction trace functionality. So here I can actually just run a transaction, and here I'm doing cast run and then the transaction hash. This hash happens to be the transaction hash of when I registered my ENS name, so it gives a lot of ENS output. And what returns is what looks like a trace. Like if you were to do trace transaction or trace block, this looks very similar, laid out in a much easier way to understand, like using that call tree. But what's going on under the hood is even more interesting, I think. So when you're talking about transaction tracing, most tools will just go and get the transaction trace from the node itself using the parity style traces. What Cast is actually doing is rerunning all of the transactions in that block in a local VM on your computer. So it doesn't use trace to get that information. It uses a combination of get block, get transaction, get storage, and get code at to actually rerun the entire transactions of that block. And it executes it locally to your environment, which allows for some really interesting properties. Now, the thing that I cheated on in that code execution was if you're pulling all of that information, it actually takes quite a while to reconstruct the block, but it caches it locally to your system, so the next time you pull it, you get sort of a lightning fast trace or lightning fast output. So I didn't want to sit here for like 30 seconds or a minute while it was reconstructing the block. But it is really interesting that you can do that without needing to have the ability to do a trace transaction on the node. And because it's doing it locally, it allows you to do something like this. So cast run, that same transaction hash, I'm adding the debug flag, and what happens is it opens up a POSIX debugger. So you can actually step through the opcodes of the contract and what's actually happening. You can see what's going on in the memory, what's getting pushed into the stack, etc. Now again, my terminal view is constrained, so there is a lot more that you can see here. But it is a really cool aspect. If you think about it, at that point, you don't need to have source code, you don't need to have ABIs. You could really go to any transaction on the blockchain in any block and really trace out what happened during that transaction. In use cases for forensic work, learning how this stuff works, seeing how contracts work under the hood, you can do this all local to your environment, like once you pull down the transaction, which is pretty cool. So again, it's happening local, it's attaching a local debugger. By the time you get to this point where it's opening the debugger, you don't need a remote connection. Because all of the information exists locally to your computer, you can just start executing without having to have like a Wi-Fi connection, for example, once everything is pulled down. So that's the overview of what I wanted to cover, right? We explored some JSON-RPC methods, maybe explored a little bit deeper than we normally would as blockchain developers. I hope I convinced you that Cast is a worthy command line tool to install and make use of. I highly recommend putting it in your toolbox. It was a game changer for me. And we did a deep dive into ENS to play with Cast and see how you could use knowledge of smart contracts to interact with the blockchain. So the next steps, use your Infura keys to plug in any Ethereum RPC compatible blockchain. So things like Aurora, Near, things like Avalanche, any of the L2s. Because Cast, because it just uses the vanilla Ethereum JSON-RPC, you can really explore this with any other chain. So taking the next step, explore other chains, and get inspired and build. I can't wait to see what you guys come up with. And that's it for me. Thank you. Any questions I can take? No questions? Cool. Well, thank you. Appreciate it.